Greetings. In this video, I'll be going through the exercises related to pairwise sequence comparison. In the first problem, your task was to go through the following accession numbers for different versions, i.e. from different species of the serum albumin protein, and using dot plots, visually inspect them for their similarity with the mouse. We had an error. I said human earlier, but the accession number was actually the mouse one. So go through and check their similarity with the mouse accession number, the mouse gene. You may find it convenient to make a function for importing the sequences and generating the dot plots, as this could reduce clutter. What is the Latin name with the form, genus, species of the animal with serum albumin most similar to that of the human? Do you find the results surprising? So in this problem, we should make a function. And here you can see this is my approach. So these lines here will create this this handle that gets opened here and closed here. And basically, these lines will be communicating with NCBI's database, the nucleotide database, and using the accession number that we provide, which we'll put here as the parameter to our custom function. So we're defining a function here that will get added to the namespace. So we'll have a user input that is this accession number, and this then gets used in calling this database accessing handle. And of course, we're using, again, Biopython. So I will need to include an install line here. Let's just, and we'll need this entrez module from Biopython. And the output of the function, this return statement here, this will simply return the translated sequence. Now, why is it translated? So we have, once the handle is open and we're communicating with the database, we have this Biopython read function here, which will go in to the handle and fetch the data that's stored there. And the data that's stored there is a record. So there's a lot of information associated with it. If you remember, we can print out whole records. For example, here. Here we can print out an entire record. So we don't want all of this information. We just want the sequence, and Biopython's objects allow us to use methods that fetch information from those objects. And one of those methods is the seek method. So we can fetch the sequence. And since this is the nucleotide database, and this is GenBank, we're getting a nucleotide sequence. So if we want a protein sequence, then we can attach another method, because the sequence object is itself a Biopython object and is subject to the Biopython methods, including this translate method, which allows us to get the amino acid sequence. So this one-liner here, although a lot is going on in it, this will let us fetch the entire translated sequence from this originally nucleotide entry. So let's try this. And I might be missing, I think I am missing another module. So to run this read function, I think we will need this seek input-output module. And then we simply need to call the function multiple times for our different inputs. So in each case, we want to fetch the protein sequence, and we want to make dot plots. So earlier in the exercise, we imported a handy dot plot generating module, which I'll show here. So we just run this line, and then this is importing a homemade dot plotting module that is based partly on the code by Miguel Rocha and Pedro Ferreira. And this will allow us to make some nice dot plots. So we'll just call this function. It takes as its inputs the window size, the sliding window. And if you remember in a dot plot, this is this noise reducing parameter that determines basically how many positions we're comparing at one time. And the larger it is, the higher the chance you have to not place a dot or reject the match, because there's at least one mismatch. So if you have a window of 3, then you have 3 positions that could be mismatching potentially, as opposed to just one. So this can be used to kind of reduce some noise, and we could play with this if we want to. And then we place in our second parameters, sequence 1 and sequence 2, the translated sequences for our accession numbers. So we got sequence 1 in all cases being the mouse accession number provided in the beginning, and then the 4 respective other species. And in each case, we're running our new function getSeq here, or getSeq, and let's hope we can generate some dot plots in that case. So here we go. And for the first one here, we can see there is some homology. All of these genes are approximately the same size, so we're looking at a diagonal basically each time, although I guess we have some overhang going on the end of this one. This one is really faint. And then this fourth one here, we see it is the strongest of the 4. So one thing we could do to find out what this one is we could simply go online to NCBI nucleotide, and we could search for this accession number. And then here we go. So, and the question was asking us what is the genus and species. So here we have the genus Rattus, species Norvegicus. So this is the rat, and it does indeed make sense that the rat would have the strongest similarity to the mouse albumin. So that is not, in fact, that surprising. One other way we could get this information, if we wanted to keep everything in Python and stay pure, is we could, instead of fetching this handle here and printing out this handle, we could replace, or yes, print out the handle and then replace this ID here with the 4th accession number. And then we would see the entire record is printed out, similar to the result that we just found on NCBI. And if we go to the very top, we will see the same information, Rattus norvegicus. So that is the answer to this first problem. Problem 2.2, make a function that calculates the scores of the following 2 alignments of these sequences using our Blossom 62 matrix. Treat all gaps with a fixed penalty of -5, excuse me, and the sequences are globins from 2 different species of worm. So here we can make another function. Let's scroll down. So this one is asking, this one is asking us, so we have 2 alignments here. So as you can see, there are already gaps that have been placed, and our task is simply to score the alignments. And one thing that we had earlier in this exercise is a Blossom 62 matrix. And the matrix is given to us as a dictionary. So it's got these braces here indicating that it's making a dictionary, and each key that's used to access a value, each key is this, in parentheses, what's called a tuple, a pair of two objects, and that pair is the two amino acids, the substitution pair. And then if you were to use this as your index, to call the dictionary, you would get back the corresponding value. And if we remember, we can try that out. For example, let's say we type in parentheses like this, W and F, and this would fetch us whatever entry is stored there. Of course, we need to run this line first. And let's see. So, and let's print it out. Why not? And a 1 is stored there. If we check, let's check F and L here. We should get a 0. And it's a 0. So you can see how this works. Whatever pair we look up, we get the score back. And so the problem is simply asking us to take these sequences and score every position in them and add that up for a total score and to compare the two. So there is, so we make another function and let's have our two sequences as parameters. And we need also a gap score. So that is not provided in the Blossom 62 matrix. So we're going to need to define that somewhere. And it's useful to let the user do that when the function is being called, because this is something that might change. And we'll just have a for loop that loops through each position in the sequence. And since the sequences are already aligned, they should have the exact same length. So, even if the sequence, the letters themselves, even if they don't add up, we should have gaps placed on the end to create exactly the same length, since this is an alignment and these are not just raw sequences. So what we can do is set up a loop that goes through every position, and that position will be determined by a range generator that goes from 0 to the length of either of the sequences, since they're the same. And then what we're going to do is keep track of every sequence, every amino acid in the sequence. So we have, in the first sequence, we start looking at these gaps at the top here. And in the second sequence, we would start looking at this M that's at the top. So we want, for each position, to look at the corresponding position in both sequences at the same time. And that will give us our pair. And then we just write it out in the same format that this Blossom matrix takes. So in order to access a value here, we need exactly this as it's written here, exactly as it's written up here, in parentheses, L and I, for example, or whatever amino acid and whatever amino acid. So we'll make this pair variable here, which is in parentheses, amino acid 1 and amino acid 2. And those are going to be changing as the for loop proceeds through. So then the only thing we need to check the only thing that's left to check before computing our scores is if there's a gap, because of course the Blossom matrix doesn't have gaps in it. So we need a conditional statement here that is just going to check, is amino acid 1 a gap or is amino acid 2 a gap? And we have to check both, because there are some positions where, say in sequence 1, there's a gap, but if like lower down, the corresponding position in sequence 2 might be an amino acid. So if we're only checking one of these, then we're going to get an error at some point because it will try to look up a pair that's like F and gap, F and hyphen, and it won't like that. So instead, we want to treat any instance of these hyphens appearing as a gap event and score it accordingly. So we set this up like so. You could also do this instead of writing or here. You could have also done an elif or else if statement here for amino acid 2. But this is just a shorter way to do it. So we include this or statement here, and it will just check, is amino acid a gap? Amino acid 1, is it a gap? Is amino acid 2 a gap? And if so, then we will increment our score by exactly the value of our gap penalty. And of course, this has been provided by the user when we made our function. And otherwise, we want to increment our score by the value corresponding to the pair of amino acids. So then we use our Blossom 62 dictionary and supply the pair in close brackets, just like we did up here in this example, except now it's going to be a variable pair that's changing with each iteration through this loop. We supply that pair, and then this becomes the score for that particular pair, and then it's added to the growing score. And of course, the growing score starts at 0, but then as we go through the loop, it will grow and grow. And then eventually the loop will finish, and at the very end, we'll return a score. So let's then run this function, and we'll set it up here. So first, let's define it. So our function is available now, and now we can call it. So I've just set up here alignment 1, C. elegans, alignment 1, Nipostrongylus brasiliensis. So alignment 1 CE, alignment 1 NB, and alignment 2 CE and alignment 2 NB. And you can see, we can just see here that they are the same size, or at least alignment 1 and alignment 1 are the same size. Alignment 2 and alignment 2 are the same size. So this is why this loop works. And we just check the score now. So we call our function, supply the two sequences. This is for alignment 1. We got CE and NB. We use a gap score of -5 as the question asked us to. And why not, we'll do the second alignment. We'll check it down here as well. And then at the end, we'll just print out both scores and see what they are. And we get these values, 309 and 189. So even though these are the same sequences, alignment 1 appears to be better scoring, at least for this particular gap score and substitution matrix that we're using. So next, the third problem asks the following. Now, to practice a bit of brute force, we will use again our sample NGS dataset, an experimental result with multiple reads or individual short sequences comprising the dataset. Let's search for the prevalence of a known reference sequence, which we expect to find in our data. And then we're given this sequence here. Use local alignment with Biopython to systematically perform pairwise alignments between the reference sequence and all sequences in the NGS dataset using a gap opening penalty of -5 and an extension penalty of -1. How many alignments have a score greater than 100? Okay, so for this one, we have, first of all, we need to fetch our data, this NGS data file. And by the way, these data files, you can see where they are if we open up the file browser in Google Colab, and we can navigate up. There's a folder called content, and in that content is we've downloaded now this bioinformatics Stockholm folder, And in there, we have a bunch of data, including our NGS data. And we can even open it up and kind of look inside it. And you can see it looks like this. It's sequences and a large header up here. Yeah, so that is the FASTA format. And then, so for this problem, we have a reference sequence. Put that here. And then we want to write a program that performs local pairwise alignment and checks which alignments have a score better than 100. So here we're using this Biopython pairwise alignment module. So let's just fetch that. And pairwise 2, as it's called, this module has a function, a submodule called align, and then a function called local ds. And this will perform our local alignment. And these Biopython functions can sometimes be tricky. So let's first of all just import our modules here. Okay, and then I wanted to show this because these can be quite tricky. So let's run help to get some information about this function because it's not always obvious what you need to run a function, and what it produces is not always that obvious as well. So this local ds, it takes as its inputs a sequence A, a sequence B, a dictionary, which is our score matrix, an opening penalty, and an extension penalty, gap penalty. Opening gap penalty and extension gap penalty. Yes, so that is how we use it. So here we provide the reference sequence as our first sequence, and an iterator that we have called sequence. And what we're doing is just looping through all of the sequences that have been fetched for us in this line up here. So we didn't talk about it much, but in addition to downloading the NGS dataset, we had a loop here earlier that simply parsed the data and created this list, initially empty, but then filled with sequence record data. So if we printed it out, for instance, we would see that it's full of all these sequences. And so this loop will go through all the sequences. The iterator will take on the values of those sequences, and at any point in the loop, we can call the variable sequence to fetch one of these many NGS reads. So this one here is not changing, right? This is our ref sec, and that's going to be the same every time. Sequence is going to change. Matchstick, here we say this is equal to score matrix. So score matrix, of course, is our blossom. Let's see. Yes, okay. And we need, actually, it is not blossom because this is DNA. So we have another score matrix that was part of the pre-code in this exercise. So we just run this, and you can see it works the exact same way as our blossom matrix, but instead of amino acids, we have DNA codes, and the scoring system just gives +4 points for a match and -4 for a mismatch. Very simple. And you can use it the same way, right? You supply in parentheses here a pair, and then you get back a score. So that's the score matrix that goes into this pairwise 2.align.localds function. And then we provide a -5 opening penalty and a -1 extension penalty for the gaps. And then this 0 on the hand here may seem strange. What happens is this pairwise2.align, it returns a list of good alignments. So you can have more than one. Usually we're just interested in the best one or the first one, so we'll put this 0 here to keep things simple. So we'll just get one alignment object instead of a list of alignment objects that will get stored as our variable test align here. And then we call this line here pairwise2.format alignment. And again, we can use the help to kind of read about this because it, again, can be a bit confusing. And this function takes as its input, here it is, align 1, align 2, score, begin, end. So the output of pairwise2.align.local.ds has this exact same format. So it will return a list. This test align will basically be a list of 5 things, and those 5 things are the first align sequence, very similar to these sequences that we provided in problem 2. They're sequences, but they have gaps in them. So you can think of them as the aligned sequence 1 and aligned sequence 2, a score for that alignment, the beginning and end positions of the aligned region. So in these, so align 1, align 2, they have the same length, right? So there's kind of a universal position scale in this alignment, and the place where matches kind of start to happen, it doesn't necessarily need to be the very beginning. The beginnings could be misaligned, especially since this is a local alignment. So we have this beginning and end then that gets spit out so that we know where the alignments begin and end. And then we just supply these different things to the function then to run the formatting. And this is going to print out for us a nice, pretty version. So we supply to align 1, test align, index 0, test align 1, test align 2, test align 3, test align 4. Just using indices to fetch the respective elements of this list that gets spit out. And then that is how we print out our formatted alignment. And then finally, we have a conditional that is just going to check, is the score, right, element 2. Here it is, 0, 1, 2 is the score. So we just check, is element 2 greater than 100? And if so, we increment a counter here that is initialized as 0. But as it goes through the loop, it will go up. And that's it. So let's run this. And our format alignment is working. So it is printing out nice, beautiful alignments that are easy and intuitive to see. And here we can see some of them have scores above 100, such as this one, and others do not. So this one had a relatively poor alignment and had only a score of 31. So at the very end, our counter is printed out, and we see that there are 236 of these alignments that meet the 100 criterion. Okay, and then for the final problem, the assembly problem. So this question gives you a set of error-free mini reads from some imaginary next-gen sequencing experiment. And so these reads, we're told, overlap. And if we look at them, that is indeed the case. So you can see this TGCTAA here is identical to these TGCTAA here. But whereas it is on the right kind of latter half of the sequence, it is on the left or former half of this sequence. And all of these sequences have similar overlap. And the question asks us to write an algorithm that assembles a single sequence from these overlapping pieces. And this is a bit of a tricky problem. So I will show my approach. And it utilizes everything that we've been using in this exercise, namely the pairwise 2.align.localDS function. So the idea here is to check the alignment of every individual in this set with every other individual. And we can do this with nested for loops, right? So we can say for each item, for example, for this guy, check your pairwise alignment with every other one. So that's, you can see how that's will be two loops basically. You can imagine like a matrix almost of pairwise alignment scores, for example, where you'd have every element of this, every one of these sequences as rows, perhaps, and every one of these sequences also as columns. And then ignoring alignments with themselves, you would have an element for each pairing, each possible pairing in this set. So that's the idea. So we have a function that we make here, and it's taking as its input the list of segments, or segs, that we call it here. And it's building a new list called new segs, which is initialized as just an empty list here. And we have the first for loop for I in the range and number of segs, and for j in the range number of segs, we want to generate an alignment. And it uses the exact same format, right? Align.localDS and first sequence, second sequence. So our first sequence is segs of I, and our second sequence is segs of j. So you can see how, as we go through the loop, first we would check, say, for segment 1 here, or segment 0 here, we would have this j loop here cycling through all the other options, checking for j equals 1, j equals 2, j equals 3, and so on. And we'd be getting pairwise alignments for each of these. And we're using the same score matrix, the DNA score matrix, same -5 opening penalty and an extension penalty of 0 here. And again, just fetching the top hit. And then here we have these 5 objects again, align 1, align 2, score, beginning, and end, which are respective positions that we can fetch from the return pairwise alignment object. And here we're just setting a threshold. So some of these alignments are really bad. And the first time I ran this, I just checked what were the relative scores. And usually if two of these sequences were actually overlapping, if we had picked like this one and this one, then their scores were better, larger than 18. And if it was just random, so some of these kind of align with each other a bit randomly, even though they're not overlapping members, those tended to have scores less than 18. So we can use this as our cutoff to select for good alignments. And I realize this is not like a super robust way to do this, but it happens to work in this case. So we'll go with that. And then we check then. So let's see if we, maybe we can print this. No, maybe not. So we'll just check two things. So there are two kind of cases that can come about, right? So imagine we align these two things. In this case, the overlap is here and here, right? And if, let's say this guy is the top sequence, then in order to have the alignment have the same kind of position scale, we would have to add gaps to the left side of this sequence, right? Because it's going to be over here, starting where my mouse is right now. And then we would have gaps extending out to the beginning of the bottom sequence. And then likewise for this sequence, because we would have this sequence on top here, we would have an overhang, which is this sequence sticking out on top, and then have gaps on the bottom sequence extending out to the end of this sequence. So where the gaps are tells you what kind of scenario you're in, tells you which direction the overlap is happening in. Is it on the left side of sequence 1, or is it on the right side of sequence 1? So if alignment 1, right, align 1, which is the first sequence, if the 0th element is a gap, and the align sequence number 2's last element is also a gap, then we're in the situation where we have gaps on the top left and gaps on the bottom right. So this is similar to saying sequence 1 is on the right and sequence 2 is on the left, or align 2 is on the left and align 1 is on the right. And in that case, we can create a new segment which is going to list in the correct order then, starting from align 2 and going to align 1, the consensus sequence that is formed by these two overlapping sequences. So we start from element 0 of align sequence 1 all the way up to the point where the aligned region starts, and then we add to that the beginning of align sequence 1 all the way up to its end. And then this would give us a full sequence with none of the gaps. Basically, it's all the letters and none of the gaps. And then we have the exact converse of this, which is simply a situation where align sequence 2 has a gap on its first element, and align sequence 1 has a gap on its last element. And this is the mirror situation where you have align sequence 1 on the left and align sequence 2 on the right. Excuse me. And then we can make a new segment that in the same way starts with align sequence 1, element 0, all the way up to the end of align sequence 2. And then we just tack this on to our growing list of new segments, and then repeat this process a few times. So in the first round, we would fuse, say, a couple segments here. So like this one might be fused, this one might be fused, and this one might be fused. We would go down from, say, 6 sequences divided by 2 into 3 sequences, and then maybe go from 3 sequences down to 2 sequences, and then from 2 sequences down to 1 sequence, kind of fusing sequences together each time. So we create basically a loop that runs this function a few times until we end with a fused final sequence here. So that is how you do it. So it's just running this function, 1 minus, or the number of segments minus 1, basically the number of kind of pairs you could make. So like there are 6 here, right? 1, 2, 3, 4, 5, 6. So or yeah, there are kind of 6 objects and 5 kind of spaces in between them, and this will be a way for us to not get an error like trying to merge the last sequence with itself or something like that. So we just do this as many times as we need to. And so this is the final result. So you can see that it starts with this guy, A, and it ends with this one here, GGGT. So that's the optional problem, quite challenging. If you had trouble with it, don't feel bad. If you did it a different way, I would be very interested to see other people's solutions. And if you can find any mistakes in how I've done this, I know this is probably not the most robust approach, actually. So I would be open to better versions. That's all for this video, and thank you very much.